So welcome everyone to our first Geospatial Forum in 2025. Our speaker today is Kyle Summerfield, who is the program manager at the 3D Visualization Center in the School of Energy Resources here at UW. Kyle has been the lead developer at the center for nearly a decade. His primary focus is on real-time 3D graphics and programming for wide-ranging platforms, dedicated virtual reality and augmented reality headsets to mobile and web deployments. Recently, Kyle has started working with UAS together with James Amato, and has tested one of their big drones to map geographic features in some parts of Wyoming. Kyle and I and Wendy Berreson first collaborated in 2015 on a fun project that developed a 3D map of a portion of UW campus using Unity 3D and City Engine. Okay. I know that Kyle spent some of his free time painting, and about 5 years ago, he did paint a flattering portrait of myself on a 24 by 36 canvas. And I wish I had brought it to share it with everyone. So I appreciate it. Yep. So everyone, please help me welcome Kyle Summerfield.
Okay. Thanks, everybody. Does that look okay up there? I am sharing through Zoom vicariously to our projector here, so it might be a little bit framey from time to time. So this talk is going to be about structure from motion algorithms generally, and two subcategories of those in particular. So I'm going to be talking about photogrammetry and Gaussian splatting. I will also touch on neural radiance fields and point clouds, but those are not the focus of this talk. If you have questions about those at any time, feel free to interrupt or throw them in at the end. Okay, so here's the forecast for the talk. I'm going to introduce myself. I'm going to introduce the Viz Center because there are quite a few unfamiliar faces in the room, although I do know a lot of you too. We're going to talk about structure from motion broadly, photogrammetry and Gaussian splatting specifically, and you're going to get a lot of slides that have too many words. But we'll spend a lot of time in each slide really digesting all of those words. Who am I? So I'm Kyle Summerfield. Again, I'm an art nerd. My degree is in fine art and graphic design. I am a tech nerd by way of video games. So I'm a self-taught developer. I'm a teacher. We run an internship program over there. Air quotes enthusiast. I have a strange career path from fine arts to computer science. So I don't purport to be an expert in any of these fields, but I am pretty functional in a lot of them. I do also own exactly one blazer, which I am also wearing now. And I am wearing for the sake of this joke, but it's really hot. So we're gonna. Okay. And then I should point out here, so there's James and I out at a mine site, some captures. That's a big old oil painting I did. That's the new drone that Paddington was referencing. This is a bunch of the Viz Center team. So that's Jerry, who's here in the room. Me, Paul and Isla are not present. James is here. And my fiance, Sabrina, is also here. Okay, so what is the Viz Center? This is just a little sizzle reel of work we've done over the years. It's approximately chronological. You can trace that progression through the migration of hair from the top of my head to the... And hopefully this looks okay. Don't frame me, I want you. So what we're looking at is the cave that's no longer present there. We did a lot of work for that environment that has been replaced with a new display that you'll see later in the slides. These are all projects we've done for departments around campus. So that was an atmospheric science project. This is a mine safety training program in VR. Sorry about the framiness. That's still being used in Gillette to train new miners right now. That was our 360 camera and me looking at a thing after the 360 camera. We do deployments for all kinds of devices. So this is an example of a desktop deployment. This is a mobile deployment of the exact same application. Insufferably framey. Here, optimized for. Yeah, but there's a lot of text. So that's our structured light scanner, output from the structured light scanner. new drone. And I assure you that under normal conditions, this is a beautiful, smooth shot. Okay, structure from motion. So broadly speaking, what we're doing is generating 3D output from 2D inputs. What we're looking at here is a sparse point cloud. So each of these points represents a tie position between two or more photos. So every point that's in here is relevant to the mapping and positioning of each of these cameras. So each of these buttons represents the position that a photo was taken from in this example. Some platforms are going to give you more information than others, so you might come in with data about camera orientation or relative position, but you can generally back engineer that using this approach regardless. So what is a point cloud first? It's just a bunch of points in space. At minimum, you need 6 floats to represent them. You need X, Y, Z, R, G, and B. So you have color values and positions. That's the bare minimum to be a point cloud. Often there's a lot more encoded there. So what is structure from motion used for? A bunch of things. So visual SLAM tracking or simultaneous location and mapping is determining your position within a space. So if I'm using my phone and I want to tell where I am with respect to the room, I could do some light structure from motion algorithms to determine where I've moved with respect to, say, that table or something like that. Plane detection. So in most AR SDKs, it has horizontal and vertical plane detection. So I can detect when there's a table or a wall. That's just running basically very light photogrammetry all the time. If you were to turn on debug for that on any deployed application, we'd be able to see those tie points being generated and discarded. Obviously, it's used for photogrammetry, which we'll talk about, and Gaussian splatting, which will be kind of the focus of this talk. But you could also use it to retexture from other sources. So for example, I've gotten way over complex meshes in the past that we needed to clean up. And so I will go in and retopologize them, estimate the polygon counts, and then just use that structure from motion approach to refine the camera positions and make a new high resolution texture on our now reduced complexity model. Okay, so this is an example of data that we have captured. These are the 2 demonstration buildings that are out by High Bay Research Facility. Each of these prisms is, again, a position that a photo is being sampled. So in this case, these are 2 videos. So we just went out there with the DJI drone, pointed it at the point of interest and said, spin in a circle, please, which we did twice. And then we feed that into, in this case, reality capture. I'll cover a bunch of software suggestions at the end. But reality capture is a great photogrammetry tool. And we'll sample at intervals. So say every 5th frame, we'll pull an image, use that as the photo input. Some of these platforms do have the ability to detect motion blur. So they'll try to find the best photos in that range. If you say, pull me 1 every 5 frames, you'll actually look at the neighboring frames and say, okay, I'll pull the clearest one within that interval. This is then the dense cloud. So we're still looking at a point cloud. This is not a mesh, but all the extra points are not really mathematically relevant. They're mathematically derived. So now we have a dense point cloud derived from our sparse one. Okay. Photogrammetry is the first subset of structure from motion algorithms I'm going to talk about. The output from photogrammetry is generally a triangulated mesh or a point cloud. The advantage of using a triangulated mesh is that we have decades of rendering behind us to relight those, to render those efficiently, to call backtracing polygons, etc. So we have a bunch of optimization that's kind of free, but long established. It can also be relit in new contexts, assuming that you perform a delighting step. Again, I'll talk about software for that toward the end. They're easy to edit and retopologize, make more efficient. They have a hard time with very thin or reflective materials. And they don't capture any of the surrounding context. So you probably can't see very well here, but there will be a closer shot later. But these wrought iron gates are just lost. They're way too thin. And the windows are also super wonky if we get up close to them, which I believe we will later. Okay, so I'm going to show you an example of some photogrammetry output and what I mean by relighting. So here we are in Unity. And this is this homestead, abandoned homestead structure out by Lightning Gorge. You can see that it appears to be quite convincingly lit. We've got bounce light. It's like we put a really nice light bake. However, that's all just in the texture. So there's no real, we can't use this with other assets because when we go to relight it, change the material here. And suddenly we can see as I move this directional light around, we have some confusing problems about how light's working in this environment. Right, so we need to perform a step to clean this up so that we can relight it for other contexts. No good place for this zoom toolbar. So here's an example of a model that has been corrected. So this is just the hand drill that's in the office. This was actually captured with a structured light scanner, but the point stands anyway. There's no self-shadowing, there's no light cast within the capture. So now I can confidently relight this object in whatever context, and it will behave as we expect. So this is a necessary step for being able to relight photogrammetry models, but it's impossible to do. Well, I won't say that. Currently, I don't know of a way to do it with Gaussian splats. Gaussian splats. So fancy point clouds. I said that we had 6 floats before. Now we're going to need a bunch more floats to represent spherical harmonics. So this is an example of that. So depending on the view angle, will be served a different color. So that means we can recycle these quads to function from different perspectives. So if I'm looking at one Gaussian splat, which are these, from one angle it might be yellow, from another angle it might be green, because that's the context. You'll get what that all means in a second here. But long story short, we're embedding a bunch of extra floats to give us information about how color should appear from different perspectives. Gaussian splatting is really powerful for several reasons. We get free reflection and refraction. We're not doing light calculation. It appears as though reflection and refraction is correct because of the positioning of those splats. But it's not actually doing any of that. Significantly lower geometric complexity, asterisk. There will come a point, there are certain circumstances where your Gaussian splat model, because your material you're trying to render is like highly transparent and then it's got an emissive thing behind it or whatever, you might end up with a more complex splat model. That's unlikely, but it is possible. And it captures the surrounding context as well, which I'll show you in a second. So this is what a Gaussian splat model looks like from the outside. So somewhere in the middle of all this mess is an actual image that we will want to look at. I'll show you the image that is in the middle of this particular one. But the Gaussians themselves are just these blurred and distorted disks. So you can imagine that they're just on a quad. They're just a Gaussian blur on a quad, and we're skewing and stretching and recoloring it to approximate what it should look like from that perspective. Here's an example of a Gaussian splat model. And this is actually up at my fiance's brother's property. This would be a real challenge for photogrammetry to render. So you can see that it captures the context pretty well. And it does a great job of getting these really thin great lines, these pipes, wiring. You can see if we look at these kind of drums here, that as I rotate it, it's so smooth on my computer, by the way. As I rotate it, the light seems to be correct for each given angle. But really all we're doing is skewing a bunch of these quads. So if I zoom out of this, there's that image that was on the slide previously. So Gaussian splatting is a process of training an AI model. So all it's doing is tweaking those positions and parameters so that it can approximate each position that you've given it and any intermediate position. Okay, so the weaknesses of Gaussian splatting, currently it's very expensive to render like per polygon. So polygon count is way lower, which I'll show you in a minute. But because we are overlaying all of these transparencies, there's a lot of overdraw happening. So we're rendering a partly transparent one here, and then one on top of that, one on top of that, one on top of that. And the final color is the one that is the mix of all of those. Right? So we're doing a lot of overdraw. But even so, it ends up being quite great. This is really a strength and a weakness. This technology is new and rapidly changing. Just this morning, I found a new algorithm that was released that I'll show you at the end of this. It can create like impressively robust image like models from 3 source images. 3 source images, I'll show you. Okay, so we've set up a web viewer at this center. So this is just running in Three.js. So if we pull up our splat model of the charbrick houses, you can see the strengths that Gaussian splatting has as compared to photogrammetry. So these fences are well captured. The windows appear to reflect and refract light as I move the view around. But no light calculation is taking place. If we have time at the end, I'll pull up some of these other models as well. Okay, let's take a look at the numbers on the output. So on the left here is a photogrammetry model, on the right is a Gaussian splat model. And we can see that the triangle count on our mesh is almost 30 million triangles and about 14 million verts. 0.5 million triangles, 7 million. So theoretically, if your bottleneck is on geometry, splatting is a much better approach. Not always going to be the case. Advantages and disadvantages. So here again, we've lost these wrought iron fences. We're getting a bunch of like kind of artifacting at hard edges that we don't have good coverage of. In this case, the facsimile of the building is much more accurate, but it's blurry, almost as though you're using Gaussian blurs to represent it. So you can see the sharpness of the text there is much better. Blurrier here. Those are the trade-offs. So the capturing approaches, I kind of assumed this audience would have some experience with photogrammetry, so I wrote this slide with that assumption, but I'll go a little bit more in depth. So generally in photogrammetry, you want 40 to 60% overlap between each image. You want enough common points between each photo to make that alignment step and get your sparse point cloud generated. You want to make sure that you have angle coverage of everything that you want to show. So if I get a nice robust set of photos for this room and I forget that there are undersides to these tables, I'm not going to have undersides to your tables. So just make sure you're considering those. If you have large uniform surfaces with no texture features, you might want to put some texture features on for it to recognize to be able to align. If it just has a bunch of frames of white photo, it's not going to be able to do anything with that. When you have things that are important to render continuously, so if I really wanted to have that picture in the photogrammetry capture, I would want to make sure that I get a straight on shot of that. The algorithms will prefer that undistorted shot. Otherwise, you're going to get this skewed, like stretched version of that if I only took photos from here, for example. As I mentioned before, modern drones with automatic focus are a huge help. So that's what we use to capture the house there. Sometimes that's not going to be possible. So we have some captures that we do in tight quarters that are just a lot of inadvisable daring do, getting drones into small places and that kind of thing. When you're doing these captures, make sure that your white balance, exposure, frame timings, whatever, all of that stuff is not automatic. You've dialed it in for your environment. However, I do kind of part ways. The common advice on the topic of autofocus. So as long as you're picking the right autofocus, you're picking the right target, autofocus is okay. If you suddenly start focusing on the grass behind your subject, you're going to have a bad time. But you don't want a bunch of out of focus images either. So finding focal depth that works for your whole capture might not be possible. In which case, autofocus is your friend. So this is structure from motion we're talking about, not structure from pivot. So if I were to, if I was in a tight confined space, wasn't able to get orthogonal shots of everything, we don't want to do this. It's better to do this, because we still have then converging focal points more commonly between the photos. So you want kind of an extended capture radius. If you want an example of using only that approach, download light fields from Steam. It's free. It's a different volumetric approach, but that's basically a capture that does this. Very convincing. Okay, in this case, in the case of Gaussian splatting, more coverage is better than more overlap. Like, not true for photogrammetry, but for Gaussian splatting, make sure you get all your angles. Have overlap if possible. The algorithm and the AI training model will do a much better job of piecing those disparate parts together, and photogrammetry generally tends to. Okay, so neural radiance fields. Has anybody heard this term? So neural radiance fields were kind of an intermediary step between photogrammetry and Gaussian splatting. They still have their place in volumetrics. The Gaussian splatting is bad at smoke and clouds and fog and that kind of thing. Or neural radiance fields still outperform it there. The problem with neural radiance fields is that you're doing a ray marching approach where you're sampling every single point along the way, whereas Gaussian splatting is actual geometry, so you might only have to sample 2 splats to get that pixel calculated. Right, so neural radiance field is they are much more expensive. However, 1 year ago, this was the state of neural radiance fields. The common training data set for these. Okay, watch this. I count these frames as we go. 1, 2, 3, 4, 6, 7, 8, 10, 11, 12, 13, 15, 16, 17. 17 images. And we got a full 3D model of this white space. It's crazy, but that's a year old and really outdated, and we can do it with 3 now. Pretty good. Okay. This is that new Gaussian splatting technique. So this literally just came out. 3 input images. Old approach, new approach. 3 images, 3 of them. This whole thing. Oh, come on. It's moving smoothly. 3 images. Let me see if I can like kind of slowly scrub it. So that... That's truly 3D. You can orbit that. You can go in there. 3 images. Okay. The other thing is the training time. So the old approach with however many hundred images, taking minutes, sometimes hours, to calculate that left model. New approach. 6 seconds, 3 images. Gaussian splatting in 3JS. So that web viewer that we set up is built on a repo by MK Kellogg that just works in 3DS. It's just kind of out of the box. You can pop your Gaussian splat in, and it will render on WebGL. The problem is, well, it's not a problem. He also has a new file format called ksplat, which is about the 10th of the size of normal Gaussian splats. Loads much faster, renders more efficiently too. It does have some sorting problems, but we'll talk about that. Okay, so this is the demo page that's set up. Has a bunch of interesting features. So if you had generated Gaussian splat and you wanted a more efficient splat model, this converter exists here. Also, there are some cool experiments. So well, that was just picking up. For the record, I did have this preloaded. This is on my laptop through with it. Styles. This is going to be kind of interesting because it's moving Gaussian splats. One of the main limitations of Gaussian splat rendering through the browser is that we're still doing CPU sorting instead of GPU sorting, so it's a little bit slower in general. But it does get the job done. What else can I say while this number goes up? Yeah, like I said, relighting Gaussian splats, I think it would be possible. We have all of the lighting information in the spherical harmonics, but you'd have to have a different lighting approach than you would take in a normal rendering environment. You'd have to be influencing those values with the position and intensity of the source. I'm sure that will get done by next week by somebody else.
The software that you're using, is it freeware or?
I have a whole slide about software.
Okay.
We'll talk about. Jump there for a second. While that's loading, I'll just say we went to a talk at GeoWeek where we actually got to see the gentleman I will link shortly, but they also gave a bunch of talks about Gaussian splatting in construction. So because it's so quick to capture, you just have to do a quick spin around. It's a really great way to capture progression of construction sites, like state of the construction site for any interested parties. Financial backers, I mean like 5%. I'm just going to endure this together. Talk about software. So software suggestions. Okay. So the software, the photogrammetry package that I've been using in all of these slides is called Reality Capture. That's installed through the Epic Games Launcher. It's free to install. Unfortunately, I don't know what their pay system is now because that before they were purchased by Epic, it was a pay to export model. And I bought a bunch of credits during that time. So the way that that paradigm works is that you can download the software, pull all of your data in, process the model, and you have to pay to export that model. Now the that house model that I showed you costs like 13 cents to export. So that's, in my opinion, much better than paying an ongoing $40,000 annual license for something like Metashape or whatever. I don't know what they charge now. Pixel, Mapper, and Matic also have robust photogrammetry tools. I'm sure several people in the room are familiar with those. The nice thing about those packages is that they can embed geolocation data right into the mesh. It is theoretically possible, certainly, to embed geolocation data into a splat. But right now, I don't see a reason to do it because the target platforms that you would be putting those into aren't going to support that rendering yet. But as soon as somebody makes a plugin for QGIS or Esri gets it in their application, I'm sure that will be a common use case. Blender, probably don't need to introduce this too much. It's a 3D modeling program, but in this context, we would be using it for editing and topology fixing and stuff like that. I have two examples of delighting software. These are both free. So Agisoft provides their delighter on that website at that link. You have to scroll down a little bit. And then Compify is a free plugin for Blender that does a fantastic job as well. This is more of a manual painting process. This is more automated. Gaussian splatting, PostShot is the one that I've been using for all of these demos. It's amazingly reliable. It's kind of shocking. I can put garbage data in there and I get something workable. Sort of the, if you wanted to build it yourself and you wanted robust controls over everything, there's a bunch of dependencies to install, but Nerf Studio is super powerful. There are plugins for both Unity and Unreal for real-time rendering environments. And then I already talked about Three.js. Checking in on our progress bar. Aha, look at that. Look at that. Okay. So they're moving nice and slowly here and very smoothly here, but you can see that they are sorting. So as they pass through the ground, we are not drawing the curtain on top of the ground, right? So we're taking care of sorting on the CPU side. And then another point I want to make is that this looks pretty amazing from here, but they didn't consider all of their angles. So I gave the example of the under table being overlooked. That's pretty common. There you go. Okay. And I'll make these slides available if you want all the links afterward. Nope. Questions? Jen?
This is all pretty cool. A lot of the stuff that I do for photogrammetry involves trying to do estimation of volumes and surface areas. But what are so your splats are those just as accurate as some of the work you'd get out of, say, photogrammetry within the photos?
Yeah, so you can think of them as accurate as the point cloud density. So measuring from, like, on a gradient of accuracy, I would say point cloud most accurate, photogrammetry next, Gaussian splats after that. Just because you're going to be shedding a lot of the point data because you don't need it all to make the visual estimation for the Gaussian splatting. But if you measured from the middle of a splat to the middle of another splat, that is a real distance that corresponds to the center of two points in a point cloud.
But you just said you weren't storing XY coordinates that were real. And so getting, like, if it's just in unknown coordinate dimensions, that might be a little tough to calibrate.
So, two things. It will be locally correct, especially if you provide some measurement to verify with. But it won't be like globally correct. So if you wanted to, if your model needed to know how far away it was from Cheyenne, you're out of luck. If you need to know how far away this is from this, you can get pretty accurate.
What about that new fancy one that only needs 3 images?
So I literally found that this morning and put it in there. The reason I was, I forgot a joke. Just a second. Yeah, this one. Okay. So this channel, it's a funny, it used to be called Nerf Guru, but Nerf became irrelevant so quickly that he changed his channel name to Pixel Reconstruct. That channel's only existed for like a year. So that's how quickly these things are moving. I think I didn't actually answer your question. What did you?
I mean, you don't have an answer because you just found it this morning to know how.
Yes, I don't have an answer. I will say, because I forgot to mention it, that this is a great YouTube channel for all kinds of volumetric captures. It covers all the different.
I mean, you do have a GIS problem.
Yep.
With some of your machines. Have you ever tried to bring some of these modules into GIS software?
So because we've been underwater with a bunch of stuff, we haven't gotten all the way there yet. But where is my viewer? Here. But this model is going to be our first geolocation test in ArcGIS, which of course is things like that.
So you mentioned earlier that how you said you told it to get every 5th frame from a video. Is there like, if you do it from a video versus 200 images, is there like preferable path? Because it feels like it might be easier just to fly and turn the camera on and record.
It is easier, but you're contending with motion blur. So it's ideal if you can get to the position, stop a second, take that photo, get to the next position, stop, take a photo. But that might not be practical. You might not actually be able to stop, really, if it's really windy. So we found, video does a great job. And especially if you have an algorithm that's going to try to pick clean frames.
What was your video resolution though? Was it?
Most of these applications will downsample the input, but it was a 4K video.
And then if you're taking those pictures, how much overlap do you still need between pictures? Especially the 3.
Well, yeah. So any questions about the 3 input thing, I'm not going to have great answers for, but I don't think I can give you a real rule of thumb. This photogrammetry, 40 to 60 is pretty standard, or even 70. But all I can say is that Gaussian splatting is more forgiving.
And then you also mentioned that the Gaussian splat does blur. the images.
Yes,
sometimes.
it's made of blur.
Can you upscale the detail using maybe the mesh? Can you combine those two and see if you can improve the quality of the visualization?
So that's actually a great question that I forgot to, I have a thing to say about that. So something I think is interesting conceptually is if you were only able to get a sparse data set, enough to make a splat, but not a photogrammetry model, could you orbit that, use those output images that have good coverage to make a photogrammetry model, and then upscale the texture? That might be a workflow that could get you both products.
When I get, you already kind of went over it, but I guess are there any general rules that don't apply from photogrammetry over to the Gaussian splat? Like, like say we went to the overlap, and then you said more coverage, more than more overlap?
Yeah, make sure you get all your angles.
Okay, so like underneath the tables.
So yeah, if you've got 128 gigs of hard drive, don't do this. Give yourself some gaps to make sure that you get all of the information you need. That's only if you have all the time in the world, get lots of overlap either way. The recommendations still work for both, but they're both structure from motion approaches.
And then you're doing the processing on the laptop or in some server?
All local. So yeah, on my laptop.
And how big is that?
Oh, this laptop is
Significant.
it's a 4090 with an i9 and way too much stuff, but you don't need all that. You could, I run them at home on my 3080 i7. We have a question in chat.
That was just me.
Oh, okay. Anybody else? Jerry?
You did mention, one of those models that you have in there that, that model was derived. And the textures, I remember some textures being derived with structured light scanning.
Yeah, that's true. So
Where does that fit in? How does that differ from photogrammetry and Gaussian splatter?
okay, so structured light scanning is more like emitting a QR code, watching how it deforms over the objects in front of it to infer the geometry. Our structured light scanner in particular is IR, so it can work in full sun. Most of them, you can actually see the projected pattern. So they need to be in kind of a light controlled environment. But the model he's referring to is this one. And I showed it because the workflow that we have for the structured light scanner has a delighting tool in it. I didn't talk about that program because it's for structured light scanning and it's also very expensive and I wouldn't recommend it really. I just have it. Yep.
So you talked about taking pictures and construction sites. What if some of the objects are moving while you are taking these photos? Is there a limitation to splatting because the object is moving while you are taking photos?
So yeah, great question. There are Gaussian splats are shockingly easy to edit. So if you end up with ghosts, in the sizzle reel, I showed this mine site that we scanned, and that was like, it was 200 ground-based LiDAR scans, and there were a ton of ghosts, and we had to manually go in there and clean up each individual that we caught that was moving. In the Gaussian splat approach, actually, I think I have a good example. So some things were moving when I did this capture, namely those two over there. And so you can see that like we get an approximation of them, but because they're moving, we don't have a lot of like facial features or that kind of thing. So this would be very easy to clean up. So if I went in and said, all right, Sabrina.
Don't do it.
I'm not used to not having a middle mouse. Sabrina? No. Oh, that's the. So if I design this program, the delete button would delete things.
You can't.
It's too powerful. But it is actually really easy to edit despite my inability to do so right. Any other questions?
I can't remember if you touched on this, because with photogrammetry, you can produce a mesh that I know you could import into Unity or Blender or somewhere to create a 3D object. Is there a workflow for that with Gaussian splats to generate
Yes.
geometry?
Well, it's kind of a complicated question because splats are geometry, but they're not a mesh hull. So yeah, there are plugins for Unreal and Unity. There is also a plugin for Blender.
Follow-up question. Is that do you find that to be a useful workflow in terms of like producing 3D objects, models for recreating?
Oh yeah, absolutely. Yeah, it's a really great way to get a fast capture of something that's going to be performant right out of the box. As long as it doesn't need to play with other asset types. Yeah, it's great.
So despite our best efforts, while taking the photo, if there is a gap, in the place, how does the Splat deal with that one if you have a hole in your data set?
So that's the worst feeling, right? You get back from the field and
Get information.
as I said, Gaussian splatting will do a better job, but it's not magic. So unfortunately, you're going to have to go recapture. You're going to have to go get more data. If that's an indoor location where you have lighting control, cool. If it's a time of day thing and a seasonality thing, you might as well just recapture.
Keep going. What about like weather? Do you want like cloudy, overcast, or does it not matter? I mean, I know that you're saying the lighting is baked in. I mean, would it be ideally like you'd be overcast and so you'd have kind of like a neutral?
I think this is a vibes-based decision. If you want a nice, bright, sunny capture, do it then. If you want something, even if you're going to delight it, if you're going the photogrammetry route and you're later going to delight it, overcast is better. Less work for you.
When same thing, I guess. Well, if it's sunny, then is your dark side going to be less detailed, I guess?
Generally not less detailed. Here. So you can see that we're still getting a lot of compelling detail. I didn't spend much time on the inside of the book. We're still getting texture detail and stuff down here. So it's just going to be different color dots.
Follow up to that, I remember photogrammetry on Ames Monument specifically. Originally, photogrammetry was done with that, if I remember correctly,
Yeah.
but then the Gaussian splatting, did the Gaussian splatting handle the lighting issues that you had?
Yeah, it actually did a much better job of resolving. So I still have that. So when we did the photogrammetry version of this, it did not resolve this area very well. It was just a big hole. So splatting did a much better job of that. We also did, for interest, I think James talked about this at his talk, but we compared still images to video for this particular model. So we have output examples for each of those.
Video was like passable?
Yeah. The video came out pretty well. I would say that the textures were sharper, but with more like gap blending in the still frames, whereas they were a little bit blurred in the video, but they were cool. Thanks, really appreciate you coming.
Our next talk is going to be on the 26th of February. So see you next time. Thank you for coming.